accelerating functional verification through stabilization of testbench using the AI/ML. The abstraction, a constraint random testbench plays a key role in the functional verification, but fine-tuning it is a non-trivial and laborious and risk-prone. Some testbenches issue can also slow down the entire verification process and make it harder to achieve the coverage closure in a timely manner. This paper proposes a methodology of adapting the AI/ML early in the verification stages of stabilize, that is, mature to the testbench faster. Using this methodology, we achieved approximately the 2 weeks of the saving, and especially through a reduction in the manual effort to write directed tests and the number of regressions to find corner cases, and 10 to 50% reduction per block of greedy resource usage. Introduction. A constraint random testbench plays a key role in a verification sign-off, but fine-tuning the stimulus constraint is non-trivial, laborious, and risk-prone. Primary source of the testbench issues such as legal stimuli, missing stimuli, and over and under bias stems from the misalignment of the implemented constraint stimuli space and the intended stimuli space. These issues can lead to longer verification cycles and reduced verification efficiency and costly debugging, and even more severe issues like bug escapes due to the omission scenarios. Testbench developers can face various practical challenges such as no visibility to constant stimuli distribution, under or over biasing, under or over constraining, evolving coverage specification, and debugging testbench failures. The current solutions, such as interactive debugging, are not most applicable for debugging or optimizing the test regression or exposing these testbench issues automatically. Given the resource and time limitation in a verification cycle of a chip, it can be challenging and time-consuming to mature testbenches that can target a diverse range of areas in the design space to find both testbench and design bugs while trying to hit the coverage targets efficiently. In project, bugs found by the designers can be broadly categorized into the following 3 categories. 1. Easy to find bugs. Usually these bugs can be exposed by a set of input or input sequences that are systematically sweeps through all input combinations. 2. Corner case scenarios or hard to hit bugs. These bugs are typically found in the following. 1. Complex logic with independent inputs. 2. The logic which requires a long loop of action to trigger. 3. Rare occurrence scenarios that may show up and disappear. 3. Data bugs. These bugs are latent RTL bugs hidden so deep that the designer would never know. Our block-level design verification environments are built through a careful consideration to hit type 1 bugs during the initial phase of project. The type 2 bugs are categorized typically needs random regression with stimuli and scenarios to hit them. These bugs are hit mostly during the late stage of project milestones, and in a few cases, these bugs escape to silicon, which must be avoided. Type 3 category bugs exist deep inside RTL and need months of regression to hit them. It depends on scenarios generation quality and delay profile, randomization, and input stimulus generation quality. The graphic processing unit (GPU) architectures are designed to have a great amount of parallelism to achieve high performance. This parallelism provides huge challenges to find bugs in small corners of complex logic, as well as closing coverage of both code and function on time. A significant manual effort is needed to write semi-directed test cases to hit corner cases at the block level and cluster level, further increasing the time taken to close functional and code coverage at the block level. Our team was exploring various functional verification solutions to shift left the functional coverage closure, so we posed the following criteria for adopting such solutions, preferably an AI/ML based A. Shift left finding the corner case RTL, testbench, and constraint issues. B. Accelerate functional of code coverage automatically. C. Help reduce the manual effort to write test cases of direct scenarios for harder to hit scenarios. D. No manual effort to rewrite or change functional coverage models. Our approach. With our goal to accelerate functional verification through the stabilize of the test bench, we wanted to share our experience for adopting an AI/ML technique such as intelligent coverage optimization (ICO) in VCS. And early in our verification cycle, ICO technology is designed to improve the stimuli quality through the diversification in the constraint stimuli space without requiring any write-all functional coverage models. We demonstrate how we leverage such AI/ML technology using multiple real scenarios case studies. In a controlled experimentation, we observed the additional 30% rate of test bench issues manifested while using ICO in a test bench deemed to be suitable of Figure 1. These additional issues comprise constraint inconsistent failures, design AVA failure due to issues in the test bench UVM driver, scoreboard checker issues, and some deadlock scenarios. Moreover, we achieved of the same 95% functional coverage, 40% faster with the ICO, that is, we met coverage with only 6 iterations of regression using ICO as opposed to 10 iterations without it. We learned that fixing the test bench issues and optimizing the regression in the late stage of the project is comparatively expensive. A method using the AI/ML that can learn and improve the stimuli on the fly by providing useful test bench analytics to the user may help achieve test bench stabilization much faster, thereby the shifting left the overall verification project cycle. Figure 1 are rare test bench issues exposed using AI/ML on a stable test bench. Figure 2 is stimuli diverse progress. In this paper, we propose a methodology for adopting AI/ML techniques such as ICO early in the project cycle in Figure 2, and we illustrate the progress of diversity, a proxy for stimuli quality. So while running back-to-back regressions, the diversity in values generated is computed as a percentage of Shannon entropy achieved over the maximum possible diversity. In practice, achievable diversity can be limited by constraint tightness. The first step is to determine the eligibility of the given test bench suitable for AI/ML application. This is done using a prognosis report that indicates whether the test bench has sufficient freedom available to diversify and bias the random value of the test bench using AI/ML. If the constraints are more directed in nature, and they can be considered tighter and have less freedom to bias as opposed to a constraint that are less directed, the constraint with more freedom that is capturing large stimuli space enable AI/ML to improve the diversification of the stimuli space. Once the test bench is determined suitable, we proceed with using the AI/ML application on the entire regression. This methodology proved to be extremely helpful in uncovering test bench latent issues, harder to hit scenarios, and exposing bugs early on. This AI/ML technology provides a qualitative assessment of the test bench randomness and the complexity of the constraint. This assessment gives us a base on which we can proceed to enable the AI/ML application for that test bench. In the figure 3, we presented the value of randomness and a value randomness as a percentage in constraint density, that is, the average number of the constraint per variable for a cache test bench. Similarly, we present data in the random block test bench in figure 4. Higher values showed which test bench are suitable for AI/ML applications as described in the next section. Figure 3, cache test bench randomness and complexity, a value of randomness, B value of randomness, value randomness, and C constraint density. And figure 4, random block test bench randomness and complexity, and value of randomness, and B value randomness, and C constraint randomness. Density. 3. Results. Overview. We will first present an overview of the result observed for 3 projects, A, B, and C, comparing the use of the AI/ML techniques in each project versus without using AI/ML, and we will discuss each project in more detail later. For Project A, we applied AI/ML solutions in late stage of the project when technology was made available to us. Surprisingly, even for the late stage of the project in which the test bench and DUT are considered stable, and we observed 30% more bugs in both test bench and DUT in figure 1, and moreover, we witnessed a 40% reduction in the number of regressions needed to achieve the targeted coverage. Encouraged by the result, we decided to adopt AI/ML solutions early in Project B. We intersected Project B's execution with the AI/ML solution and immediately started witnessing the positive impact. As shown in figure 5, we were able to uncover most of the bugs in the first 4 weeks as compared to without adopting the proposed methodology. Note, on the x-axis, we show the bugs exposed per week relative to the starting week of the 2 approaches respectively. We explained our experimental setup in more detail later. For Project C, as shown in figure 6, we compare the functional coverage rate with and without the proposed methodology on the same block in the parallel setup. With improved diversified stimuli, we were able to achieve faster coverage in fewer iterations. This helped us to write fewer directed tests, thereby saving 2 weeks of manual effort. It also helped us to optimize the regression size, enabling a 15% reduction per block of greater resource usage. We observed that the AI/ML guided to us to the shift left functional verification by several weeks consistently across the project. Figure 5 shift left project timeline with early use of AI/ML. Figure 6 accelerated coverage rate with early use of the AI/ML. The Project A, the L2 cache block detail. We provide an overview of the cache block inside the graphic IP as shown in figure 7. The test bench is implemented using the constraint randomization, where the entire function and checkers are modeled using the user-based methodology. The cache is high-performance memory with a high efficiency and low latency. The cache design also handles the entire GPU pipeline architecture synchronization functionality. A high-level test bench architecture diagram is shown below. Figure 7, L2 cache test bench environment. When we started the evaluation of applying the AI/ML, the cache feature set and the design development was completed, and the test bench environment was considered mature and stable. The pass rate for the test bench was above 98%, so furthermore, the code functional coverage was around 95%. A total of 10 regressions with and without an AI/ML solution were tried on the cache block. We found a significant improvement in verification results using AI/ML solutions as summarized as below. as summarized below. Expose scenarios not to capture as part of functional coverage figure 1. Some examples are Testbench failure 1, constraint inconsistency failures. Testbench failure 2, design SVA failures due to the issues in the testbench UVM driver. Testbench 3, failure 3, scoreboard issues related to the checker. RTL failure, design deadlock scenarios. The four incited the input stimulus distribution such as under constraint and versus over constraint scenarios. The fast coverage closure achieved 95% functional coverage in 6 regressions versus 10 regressions, saving of 4 regressions and IT resources. Project B modified L2 cache details. In Project B, we provide an observation using the AI-ML solutions on a new cache design. This was a time-critical project with a shorter runtime compared to the other project. When we ran random regressions daily without AI-ML technology enabled, we would see 2 to 3 design bugs a week. At the 4 to 5 weeks, we reserve the feature bring up and scoreboard model would becoming stable, and the random regression pass rates were nearly 98%. Encouraged by the positive impact of the AI-ML solutions in Project A, we decided to intercept this project at week 6 to enable AI-ML the solution to reform if it can provide additional value. We were truly impressed with the result of the shift left in bug discovery in this time-critical project, as shown in Table 1 and Figure 8. We summarize our observation as follows. Early bug discovery in both test and duty and quickly hitting rare corner bugs, Table 1, Figure 8. Shift left in functional coverage by 30% when coverage greater than 9%. Like Project A, we achieved the same functional coverage in 6 to 7 iterations with the AI-ML solutions when compared to a 10 iteration without an AI-ML solution. A 10 to 15% savings of grid or compute resources in Figure 9 explained later. So the Table 1 bug rate using with or without AI-ML solutions like this. Figure A is a pass percentage, B bug rate with or without using AI-ML solutions. Figure 9 is the total grid runtime per block over week, and A default 198 kilo time units, and B AI-ML 162 kilo by time unit for the same coverage. So ultimately, we expect ROI on adopting this new technology to help us reduce verification cost and improve the productivity. To measure this quantitatively, we compare the grid compute usage with or and without using AI-ML for as a block as illustrated in Figure 9. The total runtime of the simulation jobs per block was compared without or default and with the AI-ML to achieve the same coverage goal as one of the cost metrics to highlight the magnitude of the saving achieved. Figure 9 shows the default requirement of 198 kilo time units area of the bar chart versus the AI-ML solution requires a total of 162 kilo by time units, a reduction of nearly 18%. Note that the default regression was conducted by automated script, while the AI-ML regressions were conducted by the custom ad hoc script executed by multiple users. This explains the non-uniform usage in AI-ML regressions. Project C, render block details. In Project C, we present the impact on AI-ML solution on a random block where we experimented with and without AI-ML solution in parallel setup on the same block version. This block will provide blending, color, and depth calculation in the graphic pipeline architecture, the number of color format and depth format, and the type packaging combination with different register programming combinations make this design block very complex and very hard for the design verification team to cover all the scenarios. This block has approximately 350 kilo coverage planes corresponding to a various scenarios corresponding to the different color formats, depth formats, and tile packaging, so that our constraint random test benches are designed appropriately to cover all the combinations, but that would need several months of back-to-back regression to achieve the acceptable code and functional coverage. As we get close to final project mile to meet the coverage closure target, we need to put in a lot of manual effort, such as tweaking constraint to create a certain directed test cases or to change the delay profiles on each interface. All these efforts take a week or more to cover the remaining 200 to 500 beans based on how good input stimuli are generated. Table 2. Code and functional coverage with and without AIML solution on random block. As said, after the enabling AIML technology is random regression for this block, we witnessed a dramatic improvement or shift left in the functional coverage closure by 1.5 weeks. We observed that most of the complex beans which needed to tweaking of the constraint or delay profiled automatically are now getting hit quickly. Consequently, we now need to spend very minimal effort, maybe for less than 100 beans, and directed constraint tweaking or a delay profile tweaking. Table 2 shows the coverage metrics with and without using the AIML solution. Figure 6 shows the coverage acceleration with and without AIML solution. So, for conclusion, in this paper we focused on the using the AIML solution for improving the stimuli quality and early in our project, thereby achieving faster the testbench stabilization by discovering the hard-to-hit testbench bugs due to the under and over constraint and friction early on. The faster testbench stabilization early on has multiple benefits, such as finding early design bugs are less costly to fix, reducing the manual effort requiring the writing directed test cases, reducing the recognition size, and removing redundant tests, finding potentially omitted scenarios that lead to a bug escapes or coverage holes, making the test bench conducive to faster functional coverage closure. We presented the verification impact using the AIML solutions on 3 projects. Then we showed how we can achieve the improved productivity while reducing verification costs by adopting such technology early in our project cycle. This productivity and savings were achieved without putting any extra manual effort to change or rewrite any part of our functional coverage models. Okay, thank you. Today I led this paper, Accelerating Functional Verification through Stabilization of Testbench using AI/ML, Artificial Intelligence, and Machine Learning. Thank you for your time and see you next time.